Hola, good afternoon, ladies and gentlemen. I'm worse than Marco. I'm not a native Italian speaker at all. I learned Spanish about 25 years ago and spoke it fluently, pero he olvidado todo. And I speak Italian meanwhile, and if I try to talk Spanish now, it is Itagnol within a sentence. Right into my presentation, I would like to give you an overview on emission control technologies for small-scale biomass heating devices. I'm trying to give you an overview of available and not yet available concepts, technologies for emission reduction in small-scale biomass heating devices. And the non-objectives of my presentation are that this survey will not be comprehensive and full and complete. It will not be so because I would risk to miss something. So I stated from the very beginning, this is a non-objective to be comprehensive and list products. And my presentation is not intended to give any promotion to any supplier or any particular product in the field. Some words on flue gas cleaning technologies in general. These state-of-the-art for medium and large-scale combustion plants, both for biomass and solid fossil fuel installations, not only for solid fuels, but also for natural gas in terms of NOx reduction. The technologies applied there are electrostatic precipitators, backhouse filters, fabric filters, scrubbers, not only to reduce emissions, but also to increase efficiency, and selective and non-selective catalytic reduction systems, in particular to reduce NOx emissions. So far, there are only very few, if not to say no, commercially available flue gas cleaning technologies available on the market for small-scale biomass plants, smaller than 500 kilowatt thermal. The most relevant challenges that we face there are changing raw gas concentrations and raw gas composition. I will drop a few words on that later. High costs is common for basically all of the technologies that could be considered. Reliability is so far rarely proven, and maintenance is a big issue. The potential flue gas cleaning technologies for small-scale plants are oxidation catalysts, and I would like to add, not as standalone concepts, but only in combination also with primary measures, and I will give an example on that later on in my presentation. It's particle abatement technologies such as electrostatic precipitators, fabric filters, cyclones, and condensation heat exchangers will not be part of my presentation. Cyclones because I guess they are not appropriate for small-scale plants, and condensation heat exchangers are something that is linked basically to efficiency increase, but the potential to really reduce emissions is quite limited to very big-sized particles. Scrubbers would be a potential technology, also with some limitations on particle size that can be reduced, and catalytic or non-catalytic DeNOx concepts could be applied, especially when burning agricultural fuels. The fields of applications of particle abatement technologies should be differentiated when looking at small-scale technologies. The minimum differentiation is given here. We need to differentiate between manually operated combustion appliances that require quite a bit of different approach than automatically operated combustion appliances. And within the two different fields of technology, I would additionally differentiate amongst the manually operated combustion appliances between room heating systems and low-tech firewood boilers that are usually operated without, fancy control concepts, and state-of-the-art or high-tech firewood boilers. For the latter, For the latter, electrostatic precipitators will definitely be the technology option of choice, whereas we would propose that, and it is based on experience on our own R&D activities for industry, that oxidation catalysts in total have the highest application potential for room heating systems and low-tech firewood boilers. For automatically operated combustion appliances, I would differentiate in size. Electrostatic precipitators are most likely the only technology suitable in terms of economic constraints for boilers smaller than 100 kilowatt thermal. And within the range up to 500 kilowatt thermal, also fabric filters might become a technological option and could become economic as well. I promised to give you an example on how oxidation catalysts could affect harmful emissions from biomass combustion. When doing so and trying to get it implemented into, here, give an example, a firewood stove, then you have to consider basically three things. First, deploy primary measure because the oxidation catalyst is selective. It either works, and most oxidation catalysts effectively work for reducing carbon monoxide emissions, but they rarely touch particulates and volatile organic compounds. So the PM issue and the gaseous organic emissions need to be resolved by primary measures. Secondly, integrate your oxidation catalyst, but take into account that the oxidation catalyst might influence the primary behavior, and especially it induces, usually depending on the technology that you use, but here you see a honeycomb catalyst, and just consider the few Pascal additional pressure drop reduced draft that has, not a too high, but it has some impact on the primary measures. The procedure as such, you need to characterize your catalyst in order to know and decide about the temperature where it should operate or where it operates best. We did so with the development of a simple characterization unit where we could mix gas composition, space velocity, and temperature. We determined the efficiency of the catalyst depending on temperatures and the parameters mentioned before. We characterized the stove and tried to optimize the combustion chamber, and finally came up with a very clear CO lambda characteristic where you find in figures carbon monoxide emissions over the air excess ratio, and qualitatively the red line gives you a characteristic temperature. And we use this characteristic temperature in order to define on where to situate the catalyst in the stove. The where has three boundary conditions. The first boundary condition is the operating temperature that yields and results in a certain oxidation effect. The second one is that you need to achieve a sufficiently high temperature during each burning cycle, during each batch, in order to be sure that all organic depositions that have been formed, soot that has been formed on the catalyst is reliably burned during one batch. That means that you should achieve at least 400, better 450 degrees centigrade on the catalyst. And thirdly, temperature must not exceed a certain maximum temperature on the catalyst in order not to destroy it. These are three temperature constraints that you need to consider when implementing the catalyst properly in your stove. The potential for that combination of not very fancy primary optimization. This is still a natural draft stove. It's just a bit of optimization of geometry and combustion air direction. And we brought down as a first step with primary measures carbon monoxide to by about 80%, PM by about 60%, and volatile organic compounds by about 90%. The addition of the oxidation catalysts helped to further reduce significantly carbon monoxide emissions and to still substantially reduce PM emissions. We were surprised by that. The explanation is that the honeycomb catalyst that we used here had some type of mechanic effect, and PM emissions, some are condensed and built deposits, which were then burned and finally removed simply as as inorganic dust friction. Volatile organics are basically not touched and affected by the catalyst. Those are the results from lab tests. The trends were perfectly also reproduced in the field with these appliances. A few words on electrostatic precipitators. There are several developments ongoing, and first market attempts, I would calling are ongoing for boilers smaller than 100 kilowatt thermal. The functions are proven in most cases under lab conditions so far. I already mentioned the challenges and would go a bit deeper here on the different dust compositions and varying composition of the dust, which is really a major issue for electrostatic precipitators. Just imagine a logwood boiler. At the beginning of a burning cycle, you have a very high organic fraction, both in volatiles as well as in the dust fraction. While when during the, say, more stationary combustion conditions, you have mostly inorganic fractions. There is virtually no electrostatic precipitator on the market yet that can sufficiently well handle both different types of, say, PM fractions, organic or inorganic. You can mostly optimize the systems only for either reducing the one or the other. This is a major issue when really dealing with electrostatic precipitators. Electrostatic precipitators are costly both in investment as well as in operation. Continuously reliable operation is not yet proven, and maintenance and cleaning is a continuous issue. Automatization is rarely done, and if so, it is costly as well. Some examples that you see here. One example of an electrostatic precipitator, the one on the left, that is integrated in the flue gas pipe, one that is integrated on top of the chimney, and the third one that is implemented as, say, add-on concept linked with the boiler, but still an add-on and not an integrated solution. Efficiencies, separation efficiencies of the three given products yield from only 12 to 17% up to 80%. These are data from field applications. There are explanations behind why each of the systems perform either so good or either so poor. But the challenge remains that so far it's really quite difficult to have electrostatic precipitators that basically are able to cover all needs and all types of PM fractions. Finally, a word on fabric filters. There are several developments going on. The example presented here was marketed, say, at very low ambition for 1 or 2 years, but the suppliers stopped marketing it as they identified several deficiencies. especially related to the combination of the integration of the control needs for cleaning that metal fabric filter. There is still a need for optimizing the materials in terms of separation efficiencies, costs, and reliability. And as most of the fabric filters, if not to say all, will be cleaned with pneumatically with air pulses, there is an interaction with the performance usually of the boiler. And either you can avoid that by the corresponding design measures, or you need to integrate it very precisely into your control concept. This is a target to be done. I'm at the end of my presentation and just want to sum up. There are technologies under development or in an early phase of commercialization. The common challenges are in stationary operating conditions that need to be treated and handled, varying concentration and varying composition of raw gas, high costs and efforts, both on maintenance and cleaning, and rarely proven reliability in the field. My recommendation and conclusion from what we have seen on the market so far and what also our own R&D experience is that deployment of primary measures, appropriate fuel choice, correct system integration, and appropriate user behavior are first choice. Secondary measures are hardly suited to overcome lost primary opportunities. I would like to end here with one final remark, and I did not touch that in my presentation, but standardization of secondary measures is highly requested if they should become a real player on the market. And I know that there are several activities going on, especially in Germany, but these need to be rolled out on a European scale. Thanks a lot.